5 things everyone should know about ancient oceans. Number 3. During the last ice age, parts of the world warmed up, then cooled down very quickly 25 times.
What we're talking about here is the so-called Dansgaard-Oeschger events, and these were recorded in Greenland ice cores as far back as the 50s, but it wasn't until the 80s and 90s when people actually started to believe that these phenomena were actually real. And so what we see in the ice core temperature record from Greenland is repeated oscillations between cold stadial events and warm interstadial events. And the transitions between cold and warm can be sort of a mean annual temperature change of more than 10 degrees Celsius, taking place in a few decades or even less. And so these dramatic warming events that you might term abrupt climate change recorded in Greenland, and they happen repeatedly throughout the last glacial period every 1 to 3,000 years or so. So essentially a team of scientists will go to Greenland or Antarctica and will spend several months to years drilling a very long, several hundreds to thousands of meters long ice core in the ice down to bedrock. They will measure isotopes in the ice, or they'll measure content of gas in bubbles trapped within the ice. And doing this, they can measure levels of atmospheric CO2 and methane, and also reconstruct changes in the temperature over the site. Ice cores give us very long and continuously high-resolution records over the last 100 to 800,000 years, but we can also use records from marine sediments, so mud that collects at the bottom of the ocean builds up over time, and we can use shells from those sediment cores or properties of the sediments itself to tell us about changes occurring in the oceans over the same sorts of time period. And we can also look at cave deposits, so stalagmites in caves called speleothems. We can use the stable isotope ratios of oxygen and carbon in those calcite deposits to look at changes in, for example, rainfall over time. And we put all this data together from different archives, and we can learn a lot about climate variability in the past. We're not sure about what actually is the primary driver of these DO oscillations. One idea is that fresh water added to the North Atlantic, perhaps through the melting of ice caps, can actually change the circulation in the Atlantic. And we know that can happen from climate model experiments. If we do what we call hosing the North Atlantic, so shoving a load of fresh water over the North Atlantic, that tends to reduce the ability for densification of cold waters, and so they can't sink to form North Atlantic deep water, and that actually weakens the overturning circulation in the Atlantic, and as a result we get cooling in the north and moderate warming in the south. And so one of the longest standing questions in paleoclimate is how do changes in the Earth's orbit around the Sun, so-called Milankovitch theory, result in the observed climate record we see on Earth, the ice ages of the late Pleistocene? And in particular, how do we explain the large magnitude of change that we get from a glacial to an interglacial period? And that's called a deglaciation. And millennial scale climate variability, the so-called bipolar seesaw, can potentially help us here, because whenever we see millennial scale warming in Antarctica when Greenland is cold, we also see a rise in atmospheric CO2. And we know that CO2 is a greenhouse gas, and we see a large rise in CO2 during deglaciation, which could help to explain the magnitude of change during that termination. And we also know that because the CO2 is related to the seesaw, and we know that seesaw oscillations are also related, or they happen at the same time as glacial terminations, we think there might be some driving force between the millennial scale oscillations and the process of deglaciation.